Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hi, are you ready to learn more about chemical reactions? Today, we're going to learn about synthesis, decomposition, and combustion reactions. We will learn more about them, more details, and we will also explore what is the driving force of these reactions. So let's go to my screen. First, we will talk about synthesis reactions. So here is a general cartoon picture. We have an element A reacting with element B to form a compound. A nice perfect example of real life is iron rusting. Now, I know it's not as easy as that. I know iron actually needs water for it to rust, but in a very simplified term, let's just say this is the reaction. So we have iron, it's combining with oxygen to form iron-free oxide, which is rust. So let's explore what is the driving force of this chemical reaction. You will first look at it and you think, well, I'm forming a solid. But then again, iron was a solid to start with. So you cannot say one solid is better than the other. Let's think for a moment. Iron is neutral here, and oxygen is neutral. And now they form an ionic compound. An ionic compound has to be made of ions, so there has to be transfer of electrons. Let's think. Iron is neutral, but then right here, iron is, let's think of a charge. What is the charge of this? I think it's 3+. And oxygen is 2- charge. So iron lost electrons. So iron was oxidized. And oxygen gained electrons. So oxygen was reduced. So it's a redox reaction. So the driving force of this reaction is transfer of electrons. This is also the reason why I wanted to choose this reaction. This was the original name, why we say oxidation is a loss of electrons, but gain of electrons is reduced. Because iron here is oxidized, iron reacting with oxygen. And this is why we have these terms. Let's quickly balance this reaction to make sure we understand it fully. I have 3 oxygens here, now 2. Let's put 2 in front here, 3 here. So I have 6 oxygens and 4 irons. All right. Okay, let's go to another example. And we have a picture. Here we have sodium metal, which is a very, very reactive silvery colored metal. And we have chlorine gas. Yellow gas, poisonous, and together they form table salt, which is, well, it tastes great. So let's write this reaction. So we have sodium solid reacts with chlorine gas to form sodium chloride, and that will be a solid. It's another great example of a redox reaction. Let's make sure we have this balanced. I need 2 over here. I need 2 over here. And let's think about, so sodium is neutral, chlorine is neutral, and together they form ionic compound. Sodium is 1+, chlorine 1-. So again, sodium is, well, sodium lost electrons, is oxidized. And chlorine is reduced, it gained electrons. So these are great examples of synthesis reactions. You will have a metal reacting with a nonmetal to form an ionic compound. And again, the driving force for this reaction is also transfer of electrons. So that might make you think, are all synthesis, or also known as combination reactions, redox? Well, the thing is almost always. Almost always. The key word here is almost. So that means not all the time. So here's an example of a synthesis reaction that is not redox. When we have carbon dioxide gas in the atmosphere and rain is falling, so here is our raindrops, they will form, where did you ever hear of acid rain? This is what it is. Acid rain is carbon dioxide gas reacting with the water droplets, and they form carbonic acid. So they will form H2CO3. And this will be AQ. This is also carbonic acid. And this is not a redox reaction. You have so what's different about this reaction with what you saw before? Well, here we have a compound combining with another compound, and they make a bigger compound. So you don't have any single atom element that's by itself. And that's the key here. So these are not redox. So let's keep going. Let's look at some decomposition reactions. So overall, cartoon picture of a decomposition reaction is we have a compound, AB, which breaks apart into elements, element A and B. A perfect example of a decomposition reaction is electrolysis of water. And you have a really nice picture here. That's what it looks like in a lab. You have water and you put a tiny bit of sulfuric acid, tiny bit, just to get the reaction going. Put electricity through it, and voila, you separate the water molecule into its elements, hydrogen and oxygen. And you can also see that hydrogen, because its balanced chemical reaction is 2, the volume of hydrogen gas will be twice the volume of oxygen gas. That's how you can quickly figure out what gas is what. Okay, so that's a nice example. What is the driving force of this reaction? And again, you should recognize that it's a redox reaction very, very fast, because you have hydrogen and oxygen, which are by themselves, elements by themselves. That means they are neutral. And water was a compound. So that means hydrogen was +1 charge here, oxygen was -2. So oxygen in that water molecule lost its electrons. So it's oxidized. And hydrogen was a positive, gained electrons, reduced. So this one is an example of decomposition, but also redox reaction. Same thing, are all decomposition reaction redox? Well, almost always, but not always, because you can have this reaction, and now this reaction, carbonic acid, can go backwards. Carbonic acid can break apart into carbon dioxide gas and water. So here's another example of your decomposition reaction that's not redox. Let's keep going. So now we're going to go to combustion reactions. So how do you recognize combustion reactions? Do you remember? You have a carbon-containing compound. Let's go here. It's our propane, carbon-containing compound, reacting with oxygen to form carbon dioxide gas and water. And here is a picture you can produce as fire. We have a balanced chemical reaction. Here it is. And the question is, are combustion reaction redox? And, well, what do you think? What do you think? Are combustion reaction redox? How do you recognize it? I'm looking at this quickly, and the big giveaway is that there's oxygen by itself. If oxygen is by itself, that means it has a neutral charge. And now, after my reaction is done, so I'm looking after my arrow at my products, oxygen is in a compound in both of my products. So oxygen is not by itself. So this reaction has to be redox. So combustion reaction redox, yes, always. And if you want to go a step further, what's oxidized to what's reduced? We have to quickly look at our oxidation number. So oxygen is 0. here it will be -2, and here it will be -2. So oxygen gained electrons. So oxygen here, it's reduced. Now we have to quickly figure out what was oxidized. So carbon charge here is +4, and hydrogen charge is +1. And now I have to go quickly to my propane, and hydrogen charge with a non-metal will be +1. So I have +1, and that means my carbon has to be some kind of a negative charge. It will be a fraction, but all I need to worry about that it's a negative charge here. And if it's negative charge and now it becomes +4, that means it lost electrons. So my carbon here is oxidized. So there we go. So combustion reactions are always redox. So I think we should summarize quickly what we learned about all these chemical reactions and what is the driving force for them. So we have double replacement reactions, and there were 3 kinds. Do you remember? Some of them were producing a precipitate, some were acid-base, which produced water, and some were producing gas. So double replacement reactions for precipitate was formation of a solid. Formation of a solid. For acid-base was formation of a liquid. For gas-producing reactions, well, of course, it's formation of a gas. And I think it's very, very important to write that double replacement reactions are never redox. There is never transfer of electrons. Okay, let's keep going. Single replacement reaction. Do you remember? That was transfer of electrons, yes? Transfer of electrons. And single replacement reactions are always redox. That's the driving force. That's why they happen. Okay, synthesis or combination reactions, and also decomposition. We can put them all in the same bunch. Synthesis and combination, these guys, it's also transfer of electrons. But they are almost always redox. Not always. So I'm going to say almost always. And if they are not redox, that will be then formation of a solid, liquid, or gas. That will be the driving force for those of them that are not redox. And combustion reactions, that is, well, they are always redox. So this is transfer of electrons. And they are always redox. Always redox reactions. Well, there you go. So now you should know your 5 types of reactions, what's going on in them, and the driving force, why they happen. And I hope you learned something new today. See you next time.